Yeah, next presentation will be from Lucas, who has been working since the beginning on the technical on the implementation of BioDynaMo, and the fantastic results in performance, all that he will show, are thanks to his continuous hard labor over the last 4 or 5 years. So Lucas, show your work.
So I need to find the button to unmute myself. So now again, second attempt, share my screen. Can you see my slides?
Yeah.
Yes.
Perfect. So yeah, good morning and welcome also from my side. Thanks all for joining this workshop. So I'm really excited to give you like a brief overview of BioDynaMo's current capabilities and an outlook of future developments. So as you probably know, and what Roman mentioned already, is that BioDynaMo is an agent-based simulation platform with 2 important properties. It has a high-performance simulation engine and a modular software architecture. So these 2 attributes set us apart from our competitors. So let me start with the performance aspect. So we developed many mechanisms to improve the performance of BioDynaMo, which clearly shows in our evaluation. So the evaluation demonstrates that BioDynaMo is up to 3 orders of magnitude faster than state-of-the-art software, and that it scales very well across a large number of CPU cores. So this scalability test was run on a system with 72 physical cores and 144 threads. Furthermore, we demonstrated that BioDynaMo is capable of simulating 1 billion agents on a single server in several hours. So this means that 1 iteration of 1 billion agents requires between 7 seconds or 80 seconds in this use case. So if a simulation executes in minutes instead of days, this opens up countless opportunities. So it means that it is possible to simulate larger and more complex models, but there is more. So simulation development follows an iterative process during which the simulation is more and more refined. So thus, with BioDynaMo, these cycles can run through much faster. So the same principle also applies to parameter space exploration. So finding the parameters that minimize an error function, for example, to fit the simulation to some ground truth. And lastly, the more effectively the hardware is utilized, the less costs are incurred. So on this slide, I want to highlight BioDynaMo's modular software design. So at the top, you can see selected classes of BioDynaMo. The ones in white and in green are part of the BioDynaMo installation. And at the bottom here, you can see different use cases in the domain of neuroscience, oncology, and epidemiology. So classes that match the color of the heading were added to implement this specific use case. So for example, for the epidemiology simulation right here, we added simulation-specific parameters. We added 3 new behaviors for infection, recovery, and movement. And we added a new definition of an agent to represent a person. So this figure gives an overview of BioDynaMo's features and the different abstraction layers it is providing. So let's start at the bottom with the hardware. BioDynaMo is predominantly executed on multi-core CPUs, but is also able to offload specific computations to the GPU. We currently support Linux and macOS operating systems and rely on a bunch of third-party libraries. So BioDynaMo provides a rich set of low and high-level agent-based features. The low-level features are mostly hidden from the users and include parallelism and thread safety, performance optimizations, GPU support, then very important visualization, like web-based interface, which I will show a bit later, the ability to back up and to restore a complete simulation, and the whole infrastructure to ensure high code quality. The high-level layer contains features that are commonly used in agent-based models across several domains. This includes the generation of agent populations, agent reproduction and mortality, the ability to search for agents which are in my local neighborhood, the ability to simulate processes that happen on different timescales, the ability to influence the execution of the simulation while it is running, analyzing the simulation outcome statistically, parameter management and optimization. So Ahmed will later talk about this part in more detail, hierarchical model support, hybrid modeling, and space boundary conditions. So on top of these generic features, BioDynaMo offers model building blocks to simplify the development of specific simulations. So these building blocks are specific to one domain, for example, to neuroscience, for example, neuron soma, neurite element agents. So as you can see from this vertical extension here, users benefit from all generic agent-based features, even if the model building blocks are not available for a specific use case. So now I want to demonstrate BioDynaMo's capabilities. So a great way to learn a new software package is to follow examples. So to that extent, we provide demos and notebooks. So notebooks are a great educational tool to teach users various aspects of BioDynaMo. We have currently 15 different notebooks that cover various topics. So let's investigate, for example, how to create agents in 3D space. So what you're seeing here is a static version of the notebook. That means you can see the results of the computation, but you cannot change it. Let me also emphasize that we are using the web browser here, so you don't need a local BioDynaMo installation. So let's dive into it. So here we create a function that creates one agent, sets its diameter, and adds it to the simulation. Here we have a bunch of helper functions. And in this paragraph, we tell the user how to create agents which are randomly distributed in a 3D cube. So although this is a static notebook, the visualizations are interactive. Here, there are many more examples how to create agents in 3D space with different properties. So let's have a look at our demos. So we use demos for more complex examples that include either more code or require more sophisticated visualization. So for me, the best way to learn is to experiment and to play around with an example. So let's take a look at the pyramidal cell demo. So what you can see here is a new feature that we just added this morning. It's called Gitpod integration. And Gitpod is a remote development environment which is accessed through your browser. So as I speak, Gitpod is creating a new cloud instance and is loading the BioDynaMo image that we pre-built. In this image, we already installed BioDynaMo, all its dependencies, and sourced this PDM to set up the environment. On average, load time of this image is around roughly a minute. So all interactions will happen through the web browser. So this means that we can use BioDynaMo without a local installation on our system. Consequently, we can use BioDynaMo from operating systems which we not yet supporting officially, for example, Windows or Chrome OS. So everyone can use the Gitpod service free of charge within 50 hours per month. So all the user needs to do is to sign in with the GitHub, GitLab, or Bitbucket account. So now we can see that the BioDynaMo image has been loaded already. We can see the VS Code editor, which is a full-featured development environment. we can see the BioDynaMo welcome page here in the center, like an explorer to the left, and the terminal at the bottom. So the welcome page already reflects the information that we want to try out the pyramidal cell demo, and it gives us further instructions on how to proceed. So it tells us to change into the pyramidal cell directory on the terminal and to open the README file for further instructions. So the README is specific to a simulation and tells us what to do. So here it tells us to, in order to compile and run the simulation, to use BDM run in the terminal. So let's type this and hit enter. So in the meantime, I give you a very brief overview of the underlying simulation code. Let's have a look at the main function here. So here it shows that we're using the BioDynaMo neuroscience module, that we create a simulation object, that we create an initial neuron at this position, like just the cell body and 3 dendrites, and that we create extracellular substances which will later on guide our dendrite growth. So this concludes the setup of the initial model, and the next code line tells BioDynaMo to execute this model for 500 iterations. So if we look back to our terminal, we can see that like in this short amount of time, like the simulation has been compiled already successfully, and also the simulation has been completed successfully. So that was pretty fast, I would say. Let's have a brief look at the resources this machine is giving us. So here we can see that we have access to 16 threads, which is more powerful, I would say, than my local laptop. Okay, now we have run the simulation. So the next step would be to look at the visualization. So therefore, let's go back to the README and see what to do next. And it gives us instructions to use this ParaView command. So ParaView is a visualization library. So let's see. Well, let's take a step back. So maybe you know, like ParaView is a desktop application which requires like a graphical user interface, and like here we are inside like a browser. So how is this going to work? So let's see. So this is the beauty of like the Gitpod integration solution. So Gitpod offers the feature to connect through a VNC connection inside the browser to a graphical application. So this is a full-featured desktop version of ParaView, like the same that you would install locally. But again, let me emphasize that everything is happening inside the web browser. You don't need a local BioDynaMo installation to follow these steps. So now we can use all the features of ParaView to explore what happens during the simulation. So let's go to the beginning, to the initial state where we said we just create a single neuron soma at like a specific position. And then let's see what happened during the simulation. So how the dendrites grew, bifurcated, and branched. So of course you can interact, and there are many more features, but unfortunately, like with this limited amount of time, this brings me already to the end of my demo. So we have seen how easy it is to get started with BioDynaMo. It's like from 0 to like a simulation visualization in under 5 minutes.
Thank you, Lucas. I'm very impressed with this latest stuff with Gitpod.
I have a bit more
you're not
slides if I have time. So yeah, for more information about the current state of the project, I would like to refer you to our publication in the Bioinformatics Journal. And like very briefly at the end, like an outlook of what is coming. So several of the presented features are still in our development version, but they will be released next week. Afterwards, we'll focus on 2 major features. Tobias will improve the continuum-based modeling, which is often needed alongside the agent-based approach. So he will tell you more about that in the afternoon. I think his talk is at 15:10, so make sure not to miss it. And I will focus on the development of the distributed runtime. So currently, BioDynamo can be run on like a simulation only on one server, and the distributed runtime is necessary to connect multiple servers together and use the combined processing power to solve an extremely large simulation. So let me summarize. Due to our tireless efforts, BioDynamo is capable of simulating billions of agents in a wide variety of research fields. Performance is not only important to simulate large-scale models, but also to explore parameter spaces and to support rapid simulation development. So we added numerous new features and we improved ease of use and documentation. And with that, thank you for your attention, and I'm happy to take any question you may have. Thank you.
Great, thank you very much, Lucas. I think we have almost no time, but I think one question we could take if someone has an immediately, maybe that doesn't take too much time to clarify. Please raise your hand. Yeah, I see. Does anyone raise his or her hand at the moment? I cannot see all of them at the same time.
I think
yes,
Julian,
yes, Julian.
Yeah. Thanks a lot for the talk. Now, it's a very quick question, very naive, but when last year I tried some simulations with agent-based modeling, the bottleneck was the memory, because I mean, the more agents you have in your simulation, the more memory you need to use to store the information about them. And we're just wondering, how is this an issue in your framework, or what are the minimal, let's say, memory capabilities that you need to have in your computers, in your hardware to run, for example, with billions of agents?
Let me bring up this slide here. So it really depends on how many agents you have in your simulation. So here we have, for example, like the single neuron with like 1,500 agents, and then you need like less than 400 megabytes. But like with a billion, you would need like 400 or 500 gigabytes. So at the moment, like you need like this powerful machine in order to simulate 1 billion agents. But once the distributed runtime is ready, you can also like connect like less powerful machines together and then solve the same simulation, let's say with like 5 less powerful machines.
Okay, so it's essentially it is fundamentally an issue that you can solve by like distributing, for example.
Exactly, yeah. And we do a lot of optimizations because like the agent-based workload is like, I would say, fundamentally memory bound, because the operations of these agents are like simple, and there is like a lot of them. So yeah.
Okay, thanks. That's helpful to know.
Thanks a lot.